All right, as for today, we're going to continue on our path through identities and really getting much more familiar with reciprocal rules, definitions involved with trigonometric functions, breaking down quotient rules, using identities, all right? And all the while refreshing on algebra concepts and how they apply to trig. Because if you notice, all we do is we're just doing a bunch of algebra, but adding a trigonometric function into it. In our basic 5 techniques, all right, technique 1, sine, cosine, okay, that's trig. Technique 4, using definitions and identities, that's trig. Common denominator, factor, and conjugate are all algebra ideas. And it is this concept that, why did you learn algebra for 10 years before you learned trig? It's because it just keeps coming back, all right? We get the further and further in math you go, the more and more we use that stuff. Now, trig adds a fun little twist on it because now we're dealing with tangent of theta, and then all that stuff is happening, right? So trigonometric function of an angle, and then all these algebra rules encompassed. But it all keeps coming back to algebra, right? We remember the algebra prayer, or at least the end of it. Derivative, integral, and then what's the big part? Holy algebra. Okay, because it's all back to algebra, no matter how far in math you get. Okay, so I have this equation I wanna see if I can mess with and simplify. Couple things, let's identify what kind of jumps out, all right, along with our techniques. What are 2 things that definitely jump out to us? 2 possible approaches, and doesn't matter which one we start with.
The fundamental identity.
Fundamental identity, that's a big one in there. All right, the fundamental identity of trigonometry is sine squared theta plus cosine squared theta equals 1. And I see a version of that right there. Oh, so that's really good news. Okay, what else kind of jumps out? Factoring. Why do you say factoring?
You take the tan theta out, then you have the sine and sine minus 1.
And sometimes it's hard to see that with trig. So a little technique is substitution. So not everyone can see that, oh my gosh, I see, maybe I should pull a tangent out or something like that. So let's just do something easy. Let x equal sine theta and let y equal tan theta. We only have sine and tangent here. So now notice what this becomes. And it's a lot easier to see something like this, all right, when we've identified, when we put it back in completely into algebra terms. And yes, absolutely, Galen, you're dead on. In the denominator, let's pull out a y, which is tangent. And that leaves x minus 1. In the numerator, can I do something?
X minus 1, x minus 1.
Almost. X minus 1 times
X plus 1.
x plus 1. That is a difference of squares. Right? That is the definition of a difference of squares, right? So, all right, a difference of squares is one of our very like kind of quintessential ways of pulling apart two terms in a quadratic. And then now that I have it in this form, then do we see something we can do?
Get rid of the x minus one.
The x minus ones cancel. Leaves me with x plus 1 over y. Now, all right, algebraically, I'm done. So probably what should we do?
Switch back to your trig function.
Switch back to the trig functions. And so now, absolutely, if you can pull this apart when it's in its trigonometric equation, fantastic, that's better. Okay, because we don't have to convert back and forth. But this is a pretty common technique. All right, substitute it in temporarily, get it down to what we're really familiar with, our algebra. All right, pull stuff out, and then once you're like, okay, I don't see anything, I don't see anything that helps me, turn it back to our trigonometric functions. Now, once I'm here, anything else I can do? I mean, I could leave it, but I could also see if maybe I could simplify it just a touch. I don't like tangents. If ever possible, what do we always want things in? Sine and cosine. So it might not help. That might be as simple as it gets, but let's just see. And this was just a simplify, all right? So it didn't actually have an end point where I was actually going. And this does bring up one more little key piece of algebra just to see if I can do anything, I don't know. When I have something divided by something, leave it, change it, multiply by the reciprocal, leave it, change it, flip. And actually, I was like, now I see I can do a little bit of canceling. So instead of having basically this as an entire fraction, I am going to be able to simplify this down just a touch. Just because we're trying to go as far as we possibly can. Once again, now I see something else that cancels. And so I'm left with cosine. And then I could leave this as plus cosine over sine, but whenever possible, reduce it down to a single trig function. What is cosine divided by sine?
Cotangent.
Cotangent. So instead of leaving something as division, you want to get things to the simplest algebraic operation there is. So even though it wasn't massively complicated at this stage right here, I mean, that's pretty simple too. I was like, I just kind of want to keep messing with it to see if I can get it even easier. And I did. I was like, I don't even have a division anymore. So the goal is to always simplify as far as you possibly can. Now, establishing identities tell you where you should stop. And so that's kind of the nice part about establishing an identity versus we're just simplifying to see as absolutely far as we could go. We okay there? Okay, so back to our establishing identities. So establishing identities are actually really, really nice because you have a starting point and an ending point. Now, it doesn't matter if it's the left or the right side. The main idea is start with the most complicated side. It doesn't matter if it is on the left or if it is on the right. If you start with the most complicated side and you simplify that as far as you can, then move to the right side and simplify that until basically both sides are equal. That's the idea. Because I'm trying to show that one side is equal to the other side. Now, as a side note, be very, very aware, all right, on your activities, on your home phone, on everything, all right, that this is, you know what the answer is. The point is to do a step, right, and then we explain the step. And we don't just do magic math where, oh, I know what the answer is. Oh my gosh, this equals this. Oh, I'm done. Or junk in between, this equals this. All right, you have to make sure you know what you're doing because when the ones that come that say simplify, you want to make sure that you can simplify that down. All right, rewriting sums and differences, right? Single quotient, rewriting with one side terms of sines, cosines. Again, all right, our techniques, all those same techniques, keep applying. And the big thing is keep your goal in mind. So that last one, we didn't have a goal. So I just kept going until I could get it as simple as possible. But sometimes it's possible to simplify past the goal. All right, so we want to just keep going and make sure that we end up at our at the side of the identity that I'm trying to get to. All right, so we have 3 identities here, and I'm pretty sure looking at all 3 of these, we can identify which one is the more complicated side on all of them, right? Because if I start on the right side of all of these, there's not much to do. 2 times cosecant theta, what is the only thing I can do with that? Yeah. What does cosecant become? Anyone want to help Jada out? No one knows? There's a funny piece of paper everyone should have. It should help. Charlene? Are we lost? What does cosecant become? 1 over sine. That's how we graph it. Right? How do you graph cosecant? You have to graph sine first because it's the reciprocal. The reciprocal identities are the most important, right? In our phrase, SOHCAHTOA. Right? What are those 3 SOHCAHTOA? What are the 3 trigonometric functions in it? Sine, cosine, and tangent. That means secant, cosecant, and cotangent are the reciprocals because they're not even in the statement, which means in order to identify the other 3, they're always the reciprocal. Knowing the reciprocal identities are crucial because there's no other way to find them. I was like, you identify the main 3, SOHCAHTOA, and then reciprocal to get the other ones. Are we okay? That was like day 1. That worries me a little bit. Okay, so let's take a look at this. All right, so starting with the left side on what we're calling A here. With all these negatives, what springs to mind with negative angles? What wonderful property do we have to deal with negative angles? Go ahead, Jada. Even and odd, absolutely. Sine theta is odd. Cosine theta is even. Now, here's the best part. The negative comes out front, but what sine theta squared actually is, we can actually rewrite this. Because remember that notation actually says this. And some people write it like this always because it's just more descriptive. This is shorthand notation, putting the squared in between the sine and the angle. But it's actually sine of negative theta quantity squared. So the odd property says that negative comes out front. But, all right, a square of a negative is then positive, which then makes this become sine theta quantity squared, which then I could rewrite as sine squared theta. So it's important to understand what this shorthand notation is, because again, it's supposed to be, oh, it's really cleanly written, so you don't have to write this extra set of brackets and then sine theta quantity squared. But if you ever get confused, I recommend go get out of the shorthand. And it's the same thing that we did with natural logs, right? So remember your algebra. Quantity ln of x squared, we used to write as ln squared of x. So that notation is not new, but it means the same thing. Okay, so with our even and odd properties, this becomes sine theta squared. And then cosine is even. So what happens to the negative with even functions? Does it pull out to the front? Like with odd functions? No? What happens with it? You just drop it. It's even easier. All right? The negative, actually, because it's even, technically what happens is that negative becomes a positive. So that becomes cosine theta squared. Sine theta minus cosine theta. So with even and odd properties, this simplified pretty wonderfully for us. And then, once again, all right, does anyone see what's going on? So look at our techniques. Convert to sine and cosines, done. Common denominator, done. Factor, is that done?
No, not done.
So seems like I could use factor here. And this, like I said, this is the order in which you should approach the problems. Now, technically we did even and odd property first, which is kind of definitions. All right. But it just, when it jumps out and kind of hits you in the face, when I see all those negatives, all right, and we want to get rid of negative angles whenever possible. All right, let's fix that first. So actually, it looks like I could factor this. Does anyone see what this factors to, or do we need to convert to x's and y's?
A sine theta minus cosine theta.
Sine theta minus cosine theta.
Times sine theta plus cosine.
Yes. There's two pieces, right? Because I was like, that is absolutely correct. Once again, this is a difference of squares. And it's kind of indicated within it, right? I see sine minus cosine in the denominator. I mean, stuff is always going to simplify or cancel. I mean, it kind of tells me what maybe I should do. And then once again, cancels away, equals sine theta plus cosine theta. And we're actually looking for cosine theta minus sine theta. Which the only way to do that is to get to the conjugate. Unless I wrote this backwards, hold on. Sine theta, oh. I didn't transcribe it correctly. It's negative right there. Which actually means there's a negative right there. And then that means actually I need to pull out a negative here and then we're all good. Then cancel again. Now we're just canceling the other piece. And we end up with sine theta minus cosine theta divided by -1, which then flips those signs, negative sine theta plus cosine theta. And that's what we're looking for. And then just to make it perfectly match, cosine theta minus sine theta. All right. Which one did it copy? Okay. So I have sines and cosines. Once again, everything's converted. So check step 1 looks good. Step 2, common denominator. Seems like that's probably what we should do, right? We have fractions that have 2 different denominators. Now here's the trig twist. Typically, in order to make a common denominator with this, what would I do? If this was just, 1 plus x and over and y in the denominators.
Multiply by the opposite. Oh, no.
You're absolutely correct. I would multiply this one by sine over sine, multiply this one by 1 plus cosine over 1 plus cosine. But because we know we're in trig, and if I have 1 plus cosine theta, right? What can I turn that into that might be helpful? Because this also might turn into something helpful if I multiply this by a particular denominator. Does this jump out to anyone?
Almost the identity.
That is exactly correct. Because it is almost the identity, I can actually make this the identity. And so that's kind of when we're creating common denominators, instead of just doing the straight algebra approach, we put the little trig twist on it, because why not make this something that I know is going to help me, or likely. I'm not sure, but I can kind of see that I think I could turn this into the identity. So instead, I'm going to multiply this one by sine over sine. This one, because I'm trying to get a common denominator, Right, we're gonna put common denominator question mark. I want to get that close to the fundamental identity. And we said last time, cosine squared plus sine squared theta equals 1. But remember, we can kind of mess with this. And since this one's going to be sine squared, this can become sine squared theta equals 1 minus cosine squared theta. And so I can mess with this one to hopefully create 1 minus cosine squared. What do I multiply this by to make, ideally, to get 1 minus cosine squared theta? Any of our techniques jump out? Oh, this is the conjugate one. Okay, remember that's the last one you look at. But we're doing common denominator and kind of doing some other things all simultaneously. So I want to multiply this by 1 minus cosine theta over 1 minus cosine theta. And I'm doing that because I can see that I want to create a common denominator, but my common denominator is a little bit trickier than usual because I just don't think multiplying by the algebra version is going to help me at all. All right, so in the numerator of the first one, that becomes sine theta. I'm not sure I want to multiply that out yet. Let's see, cosine theta. And then the denominator, I created a difference of squares. So you can FOIL that out or box that out. But I know this is going to become 1 minus cosine squared, and the middle terms cancel, right? That's a definition of a difference of squares. So that becomes 1 minus cosine squared theta. Looks like actually on second thought, I probably am going to need to multiply this out, but that's okay. We'll do that in a minute. Cosine theta. Okay, so then I can use the fundamental identity because that was kind of the goal, all right? Using that fundamental identity in different ways is a big, big trick. So even though and so this is where I was just saying, oh, algebra, algebra, algebra. Even though we're doing algebra, it's got a trig twist on it, all right? Because I want to create a common denominator that is helpful in trig. Creating the common denominator doesn't get me anywhere if I just do the algebra approach there. All right, so then fundamental identity. And I am going to factor that in because I see that I have a positive and a negative. I have a common denominator and I could rewrite it one more step, but I can save myself a little grief. That guy's a positive sine theta, cosine theta. That guy's a negative sine theta, cosine theta. So when I write this as a single denominator, sine theta plus sine theta is, go ahead, 2 sine theta. And again, this is the algebra thing. Don't be tempted. Remember, x plus x, 2x. X times x, x squared. And I see the temptation all the time. They're like people are like sine plus sine, sine squared. Okay, remember back to the basics when dealing with trig functions, because it just adds another layer of complexity. And same thing, one of these in the numerator cancel with the square there. That gives me 2 sine over sine theta. And then what's the reciprocal of sine? Cosecant, right? That's what we started this all with. And just double check, where were we going? And we did want 2 cosecant, right? So, all right, the point is to get the left side simplified down to the right side. And that's always what we're looking for. All right, sometimes it does say, all right, want to keep that goal in mind. All right, I just simplify it down as far as I can. Sometimes we do have to back up. I was like, oh, whoops, I went too far, or I didn't quite do that the correct way. Okay, but I was just simplifying until I get to the end, till I think, oh, okay, I'm done. All right. Whoops, I called this C. Okay, so again, starting with the complicated side, the more complicated side. And looks like a couple things I could do. Anything jump out to anyone? Always start at the top of the list.
Switch to sine and cosine.
Yeah, switch to sine and cosine. All right, that's always where you start. Now, that definitely jumps out. Of all the other things, is there something else I could do?
Do you use the definitions?
There's no definition there.
Change the cotangent to tangent?
I mean, that's sines and cosines, the same thing. You're absolutely correct. I mean, and yes, technically that is the definition. There's one other that definitely should jump out of this list. Brittany, maybe you're gonna say something.
Is it identities?
Identities always involve, or the big ones involve what? Squares. In order to get to squares, what would I have to do?
Conjugate?
Conjugate. Okay. So, all right, I can do conjugate here. What is the conjugate in this case? What would I multiply by? Just so we can think about what it was.
1 minus tan theta over 1 minus cotangent theta?
Okay, first of all, I gotta be same thing over same thing. So technically, I have a choice. I could do 1 minus tan theta over 1 minus tan theta. All right, because you have to multiply by 1, so you don't change anything. Or I could do 1 minus cotan theta over 1 minus cotan theta. All right, as a note, typically, not always, when you pick the conjugate, you pick the denominator. Sometimes you're going to see that we're going to pick the numerator just because it's easier. All right, but just so you know, I could use conjugate here. Right, and I could, just because I want us to see what technique I could use. There is no common denominator here. I cannot factor definitions only in the sense that tangent and cotangent are reciprocal. So, all right, there are 2 possible methods. Which one should we choose? Should I convert to sines and cosines, or should I do the conjugate?
Sine, cosine.
Why?
It's number 1.
It's number 1, right? We start up here, okay? All right, like I said, these are in order. Conjugate makes things worse before they get better every time, okay? This is a legitimate technique. And I mean, after we're done, if we really want to mess with it, we can try the conjugate and maybe see if we get anywhere. But you always want to start with with these in the order that it's in. So let's convert this to sines and cosines. And while I'm at it, because that's going to create a bunch of fractions, let's just start writing everything in fraction form. So converting to sines and cosines. Okay, so now basically with all these things get a little bit worse before they get better. Once I have this though, now does anything jump out? So basically we go back to the list again. Okay, everything's in sines and cosines. Now what?
You leave it, flip it, change it.
Leave it, change it, flip it. That is a good call, but you can't leave it, change it, flip it with what in my fraction?
The 1/1.
An addition between fractions. You can't leave it, change it, flip it when you have additive fractions. All right? So I think leave it, change it, flip it is probably something we're going to do, but what do I need to do before that? If I have two fractions, make it one fraction, how do I do that? How do I turn two different fractions into common denominator? Oh my God, look, it's number 2. Okay, so again, it's an algebra concept. So I want to create common denominators. So this one, I'm going to do cosine theta over cosine theta multiplied by 1/1. So I don't really need to write that. And then this one, because the denominator of the entire denominator is a different one, right? So that one needs to be what? Sine theta over sine theta. So I'm creating a common denominator in the numerator, and I'm creating a common denominator in the denominator. Because again, my goal is I want to leave it, change it, flip it. But you can't leave it, change it, flip it across addition. And that's super important to know. I see people trying to do that all the time. And again, that's not even an algebra technique, that's an arithmetic technique. Okay? So you can't, but somehow when we get variables, and now with trigonometric functions, it gets even worse. All right? People are using, arithmetic things incorrectly because we have all these other pieces involved. But keep thinking back to the simple stuff. Now I can combine those, cosine theta plus sine theta all over cosine theta. Sine theta plus cosine theta all over sine theta. And again, I say leave it, change it, flip it, but if you prefer, just because I don't like, it's multiply by the reciprocal. All right, so I avoid the technical term whenever I can, just because, and this is one that, leave it, change it, flip it is something that almost everyone learns. Just, it sticks in your head. And then once again, all right, after I've done that, what do we see that looks glorious? What cancels out specifically?
Plus.
I have sine theta plus cosine, but here I have cosine theta plus sine.
Okay.
It's It's the same, right? Associative, commutative, I can't even remember the name of what the property is, all right? But that's the big thing. Don't forget the easy stuff, right? 5 plus 7 equals 7 plus 5, same. And so then we end up with sine theta all over cosine theta, which is tangent. And then let's just double check, hopefully. Yes, tangent. So again, the goal is always simplify as far as you can. Hopefully that's what you ended up with. Again, sometimes I simplify something out of my mind, man, that looks great. That's not what it was asking for. Okay, so sometimes we have to make sure that, because they're asking for something weird. So sometimes you do need to look, but all those were pretty. All those were pretty simple in what they were requesting. All right, we'll look at some other ones where sometimes it's even a decision of, do I start with the left or do I start with the right? Okay. So along those same lines, we can establish identities with inverses. So that was all directly. All right, that was using all those properties that basically, again, we covered right at the beginning of the course. Well, okay, so let's add the inverses, which is what we've been talking about this chapter. So remember what an inverse is. Tan inverse of V, right? It's its own function, but it always actually relates, right? So tan inverse of the number always actually relates back to the angle. And so the biggest thing, just like how we solve them, right? We take the tangent of both sides, right? Tangent, tan inverse are opposite functions of each other. Cosine, cosine inverse, sine, sine, etc. All right, they're all the opposite functions of each other. And so we have to get back to the inverses, in your calculator. How should I find what is that tan inverse of, 32 actually results in an angle. So to solve this, right, take the tan of both sides. And so tan theta equals V. But remember, with all trigonometric functions of an angle, we don't write them usually as a single value, but we write them as what? We don't write them as an integer. Right? So katoa. So for toa, what is it? Opposite over adjacent. Which one is that V? So what's the adjacent? It's always better to write these as a fraction. How do I know it's over 1? Why not 72?
Because then that would change the value of the V.
No, it change V. If it is written, and that's what throws people off the most. Okay, doesn't matter if it says root 5 or 7 or 11. Okay, if tan theta equals a single value, it's that over 1. All right, and that's the trick that I know seems super. It's like a simple yet hard to remember idea. All right, because again, and especially when I start putting letters in there, then everyone totally forgets. But it's always better. Trigonometric functions are something over something. even the reciprocals, right? I mean, cosecant, we always think it's just 1 over sine, but it's actually, it's hypotenuse over opposite. It's still a fraction. Once I have that, once I have the trigonometric function equals, all right, opposite over adjacent, just like we did in the beginning, what should we always do? What do trigonometric functions relate directly to? Specifically, what shape? A triangle. That means I can draw my triangle. Opposite over adjacent. And then what wonderful geometric theorem do we know to solve for the missing side? Pythagorean theorem. Oh, jeez, I butchered that. Pythagorean. Okay, got it. Let's call it H. Hypotenuse. So I can then complete my triangle. And again, because V is an unknown variable, right? I can't simplify it any further down than square root of V squared plus 1. And remember, again, algebra principle, can I just take the square root into the V squared and then square root into the 1?
Say that again?
Can I take the square root over this whole thing, individually take it into the V squared, individually take it into the 1, this becomes V plus 1? Absolutely not. All right. Just want to make sure that I see that a lot. Okay, back to what we were actually looking for. So again, I just started with the deepest inside and was kind of messing with that. But since we let theta equal tan inverse of V, and I was looking for sine tan inverse of V, that means I'm actually looking for sine of theta. And I didn't actually put my angle on here. The angle corresponding there is theta, right? Because I had to pick which side is the opposite and which is the adjacent. We just always draw it the same. So if I'm looking for sine of theta, and sine is what over what?
Hypotenuse.
So opposite over hypotenuse. Guess what sine is here?
E over square root of B squared plus 1.
Huh. So sine of theta, which is opposite over hypotenuse, which is for the triangle we just created, V all over V squared plus 1. And is that what we were trying to get? And look, establishing the identities, all right, are actually fantastic because I know the answer. Here's the question, here's the answer, or vice versa. The difference is, and my point here, okay, going from the right side on this one is impossible. All right, there's no way that I could get back to this. So, and the more complicated side is going to be the side with the inverse. So start with the side with the inverse, and then I set that up equal to the other side. But this is the big use of what inverses are, right? In reverse, you're told something, and you can identify the triangle from an inverse. We okay there? All right, let's look at some more identities. So again, establishing the identity. And we have, all right, left side and a right side. Again, in both these cases, all right, which side is more complicated?
Left side.
Left side on both of them. All right, so that means let's start with the left side. All right, and also notice that I basically ignore what it says on the right side for the moment. So I want to see what, how do we make this any better? Convert to sines and cosines. Common denominator. Done. Factor. Yeah, there's nothing to pull out. Definitions and identities. Like nothing that involves just straight sine and cosine. Uh-oh. The only thing to do here is conjugate. All right. I don't see anything else to mess with. So, like I said before, when you do the conjugate, I mean, I could pick the numerator or I could pick the denominator, and I don't know which one is best. Typically, we start with the denominator, and let's see what happens. Now, here's the other thing, and in case you weren't familiar, all right, conjugate, in order to do the conjugate, you actually don't flip both sides when you have three terms. You only flip one side. Because we want our terms to cancel, and if I flipped both signs when you have three terms, nothing would cancel just the way it would work with the signs. So in order to actually do this with the conjugate, I'm only going to flip one sign. And that may be something that you might not have seen as much in algebra. Typically, when we do conjugate, we just have two terms. But when you have three terms, you only trade one sign. Now, what do we get to do? What do I do here now?
Can we cancel?
I mean, I can, but then I end up exactly where?
The
Oh,
same
yeah,
place we
right,
started.
right.
You're absolutely correct. I was like, I can't cancel it. It just doesn't help. With conjugate, what's the next step? Usually. Right, when we did conjugate above on that half problem, kind when we were doing common denominator, where that was. So when we're doing common denominator here, we used conjugate, just kind of as a half piece. And what did we do between that step and that step?
Multiply it out.
Multiply it out. What's the technique called when you multiply a couple polynomials together? When you have two terms times two terms? What's the acronym? Has to do with saving food long term. FOIL. All right. FOIL. But this is the definition of why I think FOIL is horrible, and I never do FOIL. All right. Much, much better than that is what's known as the box method. I like the box method, and I always do the box method. Is that first term cosine or sine? And I think it's even more important in trig because we just have so much going on. Now, you want to, and the FOIL, the other reason I don't like FOIL is it only works with 2 by 2. In this case, you have to do what's known as extended FOIL, which means the acronym no longer fits. The box method, you line, and so this is, we're going to do 2 boxes. This is the box of the numerator. So you line terms up on one side, and then along the row in the column, and then multiply into each box. I like this because it also separates the terms individually. So I'm only dealing with one term at a time, and with trig, I only want to deal with one term at a time. So when I pull the terms out, I can pull the terms out just one at a time. So it looks like I have a 1 still. And the box is also nice because along the diagonals, I'll see some patterns. So along this first diagonal here, right, I have a cosine and a cosine. So that's 2 cosines. Now, it doesn't work totally, right? But I see I have a sine and a sine, so I'm going to say I have 2 sines. And then that next diagonal, I have 2 sine times cosines. And then what's left over, I have a sine squared and a cosine squared. Okay, so before we move on, this is just the numerator box, right? Before we move on, is there like a little bit of simplification I could do here?
Sine squared theta plus cosine squared theta equals 1.
Yeah, I have it right here. That is the fundamental identity, all right? And practicing recognizing that, all right? So if that thing equals 1, now look, so I have 2. Ah, so that's nice. One last step before we move on. Anything jump out?
Put 2 out.
Yeah. Well, always just keep factoring, keep simplifying. Again, I don't even know if that's gonna help me pull in a 2 doing that. I was like, but it's just so nice to keep everything as simple as you can. If you do these steps as you go, it might be helpful. Okay, that was just the numerator. Now we need to box the denominator. Now, good news, all right, that was actually the more complicated one because I know, guess what's gonna happen in the denominator box,
Negative.
right? Which means what's gonna happen?
Integral terms are going to cancel.
Yeah, by definition, we did conjugate, okay? So stuff is gonna go away here. So the denominator box is going to be simpler, right? That's why we do a conjugate. We're trying to simplify this thing. Okay, so the sign is the negative. But technically, I mean, all we're doing here, this is just algebra again. This is an algebra concept. Just with the trig twist. Okay, I wrote these not in the same order, so they're not going to cancel along the diagonals. I'll figure it out, I'm sure. Right, I didn't write them. You see, I didn't. The sine and cosine got flipped when I was writing them, so concept is still there, but they're not. It doesn't cancel as pretty. Okay, so I see sine theta and negative sine theta. I see sine theta, cosine theta, and negative sine theta, cosine theta. Okay, good. So already that's good news. Now, be careful. The box, so you can do stuff within the box, and the one thing people see, like we could have done it up here, that I have cosine squared theta and sine squared theta. So some people like to just be like, oh, that's one, and then they write it as one as you're pulling it out. And that's absolutely fine. Be careful though, because the other temptation is negative sine squared theta, cosine squared theta. Do those make one? No, right? Because that is a negative, right? And I see the temptation a lot that if you're trying to do too much, all right, you can mess up. So whatever you can, as many steps as you want to skip successfully, feel free. Otherwise, go slow. That's all. Okay, so now let's pull this out and let's see what we have. Okay, so this becomes 1 plus 2 cosine theta plus cosine squared theta minus sine squared theta. All right, I don't see a ton. And I might need to put this back together. Does anything jump out at anyone? No? Yeah, I see something that I might be able to do. So remember the fundamental identity. Fundamental identity is sine squared theta plus cosine squared theta equals 1. But also remember the adjustment of it. 1 minus either sine squared or cosine squared equals the other one. So notice I see a 1 and I see a minus. I might be able to do that, but actually I think we need to put it back together to see if that helps or not. So I don't want to just do that just for kicks. Okay, so let's put our fractions back together. Okay, so the numerator was 1 plus stuff. Cosine, 1 plus cosine plus sine. Plus sine cosine. Actually, yeah, I think this is gonna help. Okay, so that's where we sit. And I grouped that 1 minus just so we can see that it's there. I think that's gonna help because I see a cosine in the denominator, I see a cosine squared. The sign is actually messing me up. And knowing 1 minus sine squared theta is cosine squared theta, that means that's cosine squared theta plus cosine squared theta, which means how many do we have? And oh, guess what we'll be able to factor. So again, it's good to put that together because I see I have a 2 in the numerator, and that looks like I might be able to cancel that. Okay, so once again, fundamental identity. I don't want to rewrite it. Okay. So those twos are going to cancel. Excellent news. And then looking at the denominator here, what else? What do we see there? Cosine theta plus cosine squared theta. Nothing? Hold on. Okay, let's write it as such. I see that it looks like stuff might be going on. I was like, and specifically, all right, when you have four terms, all right, I'm gonna have four terms up here. I have two terms down here. Is there an algebra technique that jumps out to anyone? Let's take a sidetrack again. So x is cosine, y is sine, right? Also always recommend using x cosine, y sine because that's how they look on the graph, right? Sine is y, cosine is x. All right, so you should just keep practicing that because it keeps tracking back to what it looks like on the unit circle. Okay, now that this is written algebraically, does anyone see anything? Specifically in the denominator?
Take an X out.
Okay, all right, that's what I was trying to identify above. I can pull an x out. That gives me 1 plus x. Looking at that up here, all right, I see I have a 1 plus x. So I want to rewrite this. Because of what I see in the denominator, I'm just going to rearrange the terms in the numerator. Is there a technique that you know to factor four terms? You remember? Factoring by grouping. All right, it's basically the only way you factor four terms. You look at two terms at a time. Of the first two terms, I pull out the common value, in this case a 1. So I don't want to do this once. Then on the second two terms, what can I pull out? A y. What remains?
1 plus X.
How do you know factor by grouping worked?
See the brackets?
What's inside the parentheses match. Then I pull the 1 plus x all the way out, and what remains? 1 plus y. So this is an algebra concept that it looks complicated in trig, right? But with the algebra, I was like, as long as we remember our factoring, and factoring is a big one. Okay, we're gonna expand on this more, but we're kind of running out of time today. All right, guys. All right, so back to what we had. So that leaves 1 plus x all over 1 plus y divided by x times 1 plus x. 1 plus x's cancel. That gives me 1 plus y all over x. Convert back. Gives me 1 plus sine theta over cosine theta, and pray that's what we wanted. Yes, okay. Now, just as a note, I'm super glad that that worked because it's possible that could have been reversed, which means what would we have had to do? Yeah, okay, I could have conjugated that, but it means that our initial conjugate was wrong. Because there was a 50-50 shot we picked the wrong conjugate. I was like, I picked it because typically you do the conjugate on the denominator, but as I said, not always, right? Depends where we're going, and I had no idea to know which one was the correct one, all right? So I'm glad that that worked out. Okay, so again, factoring, all right? It is such a big thing. All right, we're gonna talk about other types of factoring next time, but always comes back to factoring. Algebra, algebra, algebra. All right, everyone, you guys have yourselves a wonderful day.
You do.